Okay, off we go. Don't forget attendance quiz, attendance code, and all that. Again, clock's ticking. Last time if I remember correctly, we just had barely started with 3.2. Yeah. Let me go ahead and just kind of start over because this is really kind of the important part of 3.2 is right at the very beginning, and the rest of it I'm going to blow through. It's pretty plug and chug. So when you have a parametric curve, right? And keep in mind that's a function. Position is a function of time. We're going to need to analyze curves. We're going to do a lot of this in chapters 6 and 7. And so we're going to need to have various objects relevant to the curve identified, named, and relationships between them established. Okay, so the first one I want to talk about is the velocity vector, and that's old news, right? So the velocity vector, r prime, is something like this maybe, right? And that represents y'all know what velocity is anyway, computed by the derivative, no big deal. Okay, related object that we have not talked about before comes from looking at this equation right here. Now, from a notational standpoint, I hope this is no surprise. After all, one way to write r prime would be dr over dt. Right? This is how we write derivatives. As it's written here, if you look at what we've got velocity, r prime, velocity times time, and that gives you displacement. So the way you think about the dr vector as a thing by itself is it's something like that. It's a vector that points in the same direction as the velocity, right? But its magnitude is sort of a differential displacement. So this point is where we were. Right, this is where we sort of start the consideration. And at this point, we know what the velocity is. We computed the velocity. And if the curve were to just continue exactly as it was, exactly at this point, with exactly that same velocity, which it doesn't. But if it were to continue with exactly that velocity, then dt seconds later, you'd be here. Right? So dr is what we call the linear estimate of the change in our position. R is position. Dr is the differential of position. Again, linear estimate of how much the position changes. For whatever it's worth, sometimes I'll refer to dr as the position differential. Again, literally what it is. R is position. D means differential of position. Okay. Is that cool? Is everybody on board with that?
Are dr and ds used interchangeably?
No, they're different. So dr is a vector. It has a direction and a magnitude. ds was the next thing I was going to talk about. So ds is just a distance. It's again a linear estimate, but it's not a linear estimate of how much my position changes. ds is just a linear estimate of how much distance I've traveled. So it's a scalar. Right? And let's see here. Let me go ahead and so thank you for the segue, by the way. It was perfect. So ds, just looking only at the estimate of how far we've moved. Doesn't have a directional aspect, but I think it's pretty believable that it's just the magnitude of the dr vector. The dr vector tells you direction and distance. ds just tells you distance. Okay. All right. So there's one other player that we need to discuss here, and that is this unit tangent vector, capital T. Very useful in a lot of different circumstances. It comes up. Again, we'll see a lot of this in chapters 6 and 7. Now, it's pointing in the same direction as the velocity, and it's a unit vector pointing in that same direction. And again, knee-jerk reactions. I hope you're all trained and have the same knee-jerk reaction. If you want to find a unit vector in the direction of a vector you've already established, then that unit vector is that other vector divided by its own magnitude. So easy to write down the formula for it. it's interesting how it relates to these other objects. Let's see here. Let me keep the color on here. T times ds gives you the dr vector. Now, there's a couple of different ways that you can see this. My favorite way to see this is to just think about vectors in terms of directions and magnitudes. And if two vectors point in the same direction and they have the same magnitude, they're the same vector. Right? If it looks like a duck and quacks like a duck, it's a silly joke. Okay, well, let's look at these two vectors. Which direction does TDS point? Well, it points in the direction of the velocity. Which direction does dr point? It points in the direction of the velocity. These two vectors clearly point in the same direction. Now let's talk about magnitudes. What's the magnitude of dr? Well, it's previously discussed. The magnitude of dr is ds. What's the magnitude of TDS? Keeping in mind t is a unit vector. Again, ds. Right? So same direction, same magnitude, same vector. Is that cool? Everybody happy with that? If you would rather see some algebra, you can rewrite ds with that formula. You can rewrite t with that formula, and then when you multiply that out, this times that, the magnitudes cancel, and you get exactly that, which of course we've already established is that. So if you want to see the algebra, that's how the algebra works. Okay. All right. That's the most important stuff in 3.2. Everything else is pretty plug and chug. So let's, again, tough choices and all that. We've got much more sophisticated stuff coming up, right, that I think our time in class would be better spent focused on. So I'm going to go pretty quickly through the rest of 3.2. Suppose you want to compute the length of an entire parametric curve. Well, I make the modest observation that you can compute on each individual piece, compute ds, for which we have a formula, right, and then just add up over the entire curve with an integral. That's all it is. We're just integrating little pieces of length to get the total length. And it's a very plug and chug formula. Notice down here, all I'm doing, given, let me get my colors straight. Given a parametric curve, compute the velocity. Don't forget to take the magnitude and integrate. Okay, so we take the magnitude and integrate. Notice we're going from t equals 0 to t equals 1 because that's what our curve is defined as. And a little bit of algebra. Here's the resulting integral. And by the way, it's a beast of an integral, right? I don't want to have to compute this integral, and I'm sure you don't either. I don't even know if it's tractable. I haven't worked it out. Doesn't matter. It's not something that's going to be convenient, and it's not something that I'm going to ask y'all to do when it turns out to be this ugly. Right? But the point is, now it's a single variable calculus problem. Okay, how are we doing? Everybody happy with that? Very plug and chug. By the way, there are some exercises in the book where you'll do this, and Kali has cleverly crafted some examples where everything works out really nicely. And it's a trick shot, by the way. It's super easy to make integrals that are outrageous. And trivial examples end up being so trivial as to be boring and pointless. And finding something exactly in between that's not trivial, but it's also not impossible. It's a very narrow little window there, and she's got some nice ones. Okay, so let's talk about parametrized curves. Y'all remember the graph parametrization, and this curve here, for example, is parametrized by that. Let me do it like so. This is a parametrization because you can plug in and that equation works. You plug in the X, plug in the Y, it works. That's a parameterization. That said, so is this. Take this X and this Y and plug into there, and that equation, it works again. So a different parameterization of the same curve. Parameterizations are not unique, and we've talked about that before. So, all right. Well, here's a different take on that. We can view this as two independent parameterizations, or we can view this as take a relationship between two parameters T and Q and just, kind of plug that into there and see what you get. And literally, plugging in this formula for T into the left parameterization produces exactly this right parameterization. So this is called a reparameterization. And all you need to do a reparameterization is you just need to have a formula for T in terms of your new parameter. Plug it on in. So, here's a new parameter that you can use. Given a parametric curve, we already have a parameterization. Position is a function of time. And by the way, we're going to set a base point. That's where we're going to call T equals 0. Let's just nail that down arbitrarily. At a given moment in time, I can compute the corresponding distance. How far along that curve have I traveled by that time T? It's literally the arc length formula from the previous page. So we have then an explicit formula that tells me S as a function of T. And then you could just solve for T as a function of S. Once you have T as a function of S, you pull this little fast one, and out comes a new parameterization. And that new parameterization is called the arc length parameterization. So when you do that, and there's various nice things about it. It turns out that the arc length parameterization is always unit speed and calculation, and this is not the point. What I think is the most important thing about the arc length parameterization is this right here. It's intrinsic to the curve. It doesn't care about, see how to say this. It's natural, independent of how you choose to think about it. So let me give you an example. This is my favorite example of an arc length parameterization. When you're driving along the road, right, you are parameterizing the road. Think about it. Position, where am I at a particular moment in time? Right, so if I drive from here to Raleigh, jump onto 40, off we go, right? I am at a certain position when I start, and then 5 minutes later, I'm at a different position, and then 5 minutes after that, I'm at a different position. At every time, there is a corresponding position. That's what a parameterization is. Now, if you drive to Raleigh, that's a different parameterization because you might drive a little slower, a little faster, who knows, right? Whatever. But so you're going to have a different parameterization because you drive differently. Here's what's intrinsic. Right? Neither of those is intrinsic to the road. Both of those parameterizations are based on us personally. The intrinsic parameterization is position as a function of distance, and they have this. And in fact, they make signs on the road to tell you the arc length parameterization as you drive. They're called mile markers. Y'all aware of mile markers? I don't know how much you pay attention to those things, but as you're driving along the interstate, every mile or so there will be a small little sign, and it just has a number on it, and it'll say 268, and then you drive another mile, 269, right? And they're literally telling you this is where you are that many miles away from some fixed reference point. And I actually don't know where the fixed reference point is. It might be if I had to guess, oh gosh, Yeah, I should look that up. It might be like the state line or something like that. I don't know. Anyway, the point is, it's literally distance from some fixed reference point. Drive however you want. Drive fast, drive slow. The positions of those mile markers is always the same. So it's intrinsic to the road. Does that make sense? Everybody see what I mean? It's intrinsic to the road. Doesn't matter how fast you drive. So it's a natural thing. It's it doesn't depend on the arbitrary way you choose to look at it or the arbitrary way you choose to drive. Okay, why do we care about arc length parameterizations? Why is it useful to have a parameterization that's intrinsic to the curve? Well, kind of abstract math reasons. If you want to prove certain theorems, it's a useful construction. Probably not exciting a bunch of y'all, if I had to guess. And that's fine. So the other bad thing about it, they tend to be hard to compute. So this example I'm going to show you here, we're going to try to do an arc length parameterization, and we've already seen that when you do an integral of a speed, right? When you do an arc length computation, you end up with a square root, and square roots inside of an integral is a bummer, right? So you all already know that. So I've gone to some trouble here to parameterize in a clever way that allows for my velocity. Right? You look at my speed. I guess that's speed squared. The thing under the radical, I've gone to some trouble to make it to where this term just turns that minus into a plus, and therefore keeps this a perfect square, and that makes the square root disappear. So this terrifying square root that we were worried about, that square root turns out to be something that we can simplify. And check it out, even with that, even having crafted a particularly convenient example, I still end up, now don't forget I've got to solve for t. And oh gosh, now I'm going to have to solve for t in a cubic equation, and that's hard. Basically, it's not feasible. So these examples tend to not work out very conveniently. So anyway, there is an example on the homework that y'all are going to have to go through. Kali found an even easier, even more convenient example where this actually does work out very nicely, where you can solve for t, and in that case, you can create the arc length parameterization. And it's just, you follow the process, plug in appropriately, and it'll work out. Okay, let's get along to 3.3. This is a very important section. We're introducing a new mathematical object. This is a very, very important mathematical object. We're going to do a lot of stuff with this. Vector fields. Vector fields are going to be the main object of study in chapters 6 and 7. Chapters 6 and 7 are what the engineering school has told us are by far the most important things in this course for engineers to understand. Right? So vector fields, kind of a big deal. Though for those of you, I know most of y'all are engineers, so it's going to be a really big deal. So let's just dive in. Here it is. A vector field is a function from Rn to Rn, and specifically, those numbers have to be the same. Now, okay, big tent, right? That's a lot of different functions. What's that got to do with anything? How do we visualize these? This is how we think about vector fields. The input you should think of as being a point in Rn, in this case R3 as I'm drawing it here. The output, same Rn, don't think of it as being a point. Think of it as being a vector in Rn. Now, vectors you can draw anywhere, but in practice, this vector is going to supposedly represent probably something that's happening at this point, and so we draw the vector with its tail at that point. Again, you could I mean, these are, in fact, the same vector, right? But to understand this as a vector field, we draw the field vector with its tail at the point. There you go. This is how we think about vector fields. Is that cool so far? For every point, there's an associated vector. Simple as that. Okay. What does this look like to y'all? Any images from the real world conjured by looking at these pictures? I'll tell you what I think of, right? I see, with this picture over here on the left, here's a vector field in 2 dimensions. I see a flow of a fluid. It's like there's maybe a river, and the water is kind of flowing sort of this way, and the arrows, wherever you're looking, whatever point you're looking at, the corresponding vector tells the velocity of the fluid at that point, perhaps. I don't know, that's just kind of what I see. Is that believable? When I see this picture right here, I don't know, everybody's mind works in different ways. What I see is there was a flock of birds on the ground, the XY plane, and then somebody scared the birds and they fly up into the air. I don't know, that's what I see. Right? So, maybe you visualize different things, totally fine, all cool. Vector fields can be used to model lots of different real-world physical phenomena. And there's lots of them, and they're different. And that's a good thing. All right, so we'll talk about some applications in a bit, and we're going to do tons of applications once we get to chapters 6 and 7. But let's get some examples under our belt. First, looking on the left here, this vector field at a given point. Here's the formula for our field vector, 2, 1. Keep in mind we draw the field vector with its tail at the point. So there, for that point, that's the corresponding field vector. Now you're going to notice the field vector is constant. It's always the same. It's always 2, 1. And so what that means is at every one of these points, we get the exact same field vector for each one of them. So this is what that looks like. What do you think? Everybody buy it? Let me observe a couple of things about this. First of all, you'll notice I only drew a handful of points, and at those handful of points are associated field vectors. Why didn't I do more? Why didn't I do all of them? And you can probably see how this would work out. If I did this for every point, then the entire picture would just be a muddy mess. And I wouldn't be able to learn anything. I wouldn't see anything from that. So you got to draw, if you want to have a good picture of a vector field, you want to draw enough field vectors at enough points that it conjures an image, but not so many that it creates confusion. So there's sort of a compromise. It's kind of like with level sets. I don't know if y'all remember with level sets. You can't draw all the level sets. The picture would just be all pencil lead and therefore pointless. Right? So you draw enough that you see what's going on, but not so much that it gets confusing. All right, next example. Let's see, let's just do it like this. There we go. Okay, next example, let's look at this one. Again, the rule is for any point, you look at the formula for the field vector, and then you draw what that field vector is. Now you're going to notice right off the bat, hey, x, y. Oh my God, look at that. The output's the same as the input. Oh, that's wonderful. We should end up with some really nice, simple picture, one would think. But you got to think it through. Be careful. What this is saying is that the field vector has the same coordinates as the input point. But the input we're thinking of as a point, as a location. So if I want to understand the field vector, I can't say it's the point, because it's not a point, it's a vector, right? So, okay, what I can do is say the field vector is the same as the position vector for that point. That is okay. And the position vector for the point is like so. So perfectly fine to say that the field vector is the same as the position vector, but of course, how do we draw vector fields? Well, we have to draw the field vector with its tail at the point in question. And so we draw it like that. What do you think? Does that make sense? Everybody's happy? Okay, so notice that at every point then, for this vector field, at every point, the field vector will always be radially outward from the origin, and the magnitude will equal to the distance from the origin. So the further you get out, the longer the field vectors are, and always radially outward. And so that you think that through in a bunch of examples, and you get this. Everybody happy? Okay, here's another thought. Y'all have heard me say this a million times. You're going to hear it a million more. You got to keep the calculus of graphs distinct from the calculus of level sets, distinct from the calculus of parameterizations, etc. Right? All these different, the connections between calculus and pictures depends dramatically on what kind of a picture are you looking at. And so we've already talked about the calculus of this, that, and the other thing. But let's talk about what kind of a picture is this. It's not a graph. It's not a level set. It's not any sort of collection of level sets. This is not a parameterization of anything. This is not a literal picture where I have the domain over here, target over there. It's none of those. Right? We previously had 4 different ways to draw pictures to understand functions. This is none of them. This is now number 5. It's a completely different kind of a picture to understand a different kind of a function. And yes, we are eventually going to talk about the calculus of vector fields. And it's completely different from any other kind of calculus that we've done. Okay, so anyways, that pattern continues. Make sure while you're thinking about things like this, make sure not to, take ideas about how graphs work and sort of speculate that these kinds of pictures will do the same. But easy example. Here we had a constant. How come the picture isn't like horizontal or something? Right, on a graph of a constant is literally horizontal. Nothing of the sort here. Right? So again, partitions in your mind between these different kinds of pictures. Okay, next example. I'm going to walk y'all through most of the ideas of this. I am going to leave an important detail for y'all to do for yourselves. Okay, here's the idea. Any given point, let's say this one. Okay. Before we move along, let's see here. I could view that point as a position vector, I suppose. Let me do this with a pen instead of the marker. Position vector. Okay. Here's an assertion I'm going to make. If I take that position vector and do a quarter turn counterclockwise, of that position vector, let's think of before I finish that sentence. How would I do a quarter turn counterclockwise? How does a rotation work? Well, don't forget a rotation is a linear transformation. Linear transformations are matrices. Matrices you can understand by their columns, yada, 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 linear algebra. Right? So this is something y'all can work out. And I think this is an excellent exercise to write down the matrix that represents a quarter turn counterclockwise. And I'm going to claim now, if you were to take a quarter turn counterclockwise of that position vector, what you would get is
that, you would get the corresponding field vector. And of course, now when we draw field vectors, we draw them with their tail at the point in question. And so we'd actually draw it like that. So this business here, about the road, I'm just going to pull it out, down here out of the way. This business about the position vector rotating to give you the field vector, this is just kind of how the algebra works out. The punchline is that at any point like this is the field vector. It's always sort of a, right angle from the radial line, and you're going to end up then with your field looking like this. Does that make sense to everybody? Now again, big step that I'm leaving for y'all, right? I want y'all to do this part. I want you to make sure that you can write down the matrix that represents a quarter turn, multiplied by x comma y, confirm you get negative y comma x. And as always, when I do these suggested exercises, if you get stuck, come talk to me. I'll be very happy to help. I want to make sure everybody can do that. So just come on into office hours. I'll be happy to walk you through it if you can't, make it on your own. Okay. Moving along. This is a really important vector field. Won't look familiar when you see it in this form. But when you do a little bit of algebra like so, that's just a little bit of algebra. Hardly anything happened. Check it out. This is a unit vector. It's a unit vector that points radially outward from the origin. And now notice the remaining magnitude is inverse square. So this is what we call a radial inverse square. Sometimes people put those in the other order, inverse square radial. Suit yourself. Sometimes people just call it an inverse square vector field. The radial is inferred by the inverse square. Anyway, very common vector field. In particular, this vector field, with that formula, all gravitational fields look like this. The gravitational field created by a point particle looks exactly like that. Electric fields created by a point charge look exactly like that. So, super important, right? It's an important vector field because it describes gravitational fields and electric fields. And, if you're going to be an engineer, electric fields, you can't get away from it. There's no way, right? Gravitational fields, you might make the case to yourself that, hey, I tell you what, I'm not planning on being an astronaut. Gravitational field is constant, gravity's down. Right? It's as simple as that, and so I don't really care about gravitational fields. That's a reasonable take, but it turns out gravitational fields are actually a fantastic metaphor for understanding electric fields. And I'm going to do a lot of this when we get into Chapter 7. The way I'm going to encourage thinking about electric fields is to understand gravitational fields first. Gravity is much more relatable. It's created by mass, which we can see and touch. Electric fields are, you can't see them, you can't touch them. Electric charges, you can't see them, you can't touch them. You get shocked every now and then or something, but it's just not as relatable, right? So I think gravitational fields are the best way to understand electric fields. That's just my opinion. Anyway, big deal. Okay, gradients. Now, y'all already understand gradients. Y'all know the formula for gradients. We know that if you're looking at a graph of a function, gradients point uphill. Direction of steepest ascent when you're looking at a graph. All right, now all of that was thinking of the gradient at one point. But here's the observation, and it doesn't take a lot of work to get to it. When you have a function, whatever your function is, when you compute the gradient, what you get is a vector field. Because look at what we got here, right? I take this function, I write down the gradient, don't plug in a single point. Think of this as a formula that tells you for any point x comma y, here's a formula for an associated vector. That is literally the formula. That's the definition of a vector field. So it's a different take on vector fields. Excuse me, it's a different take on gradient. Don't think of a gradient as something that you look at one point at a time. Think of a gradient as a vector field that that you associate to a given multivariable function. It's just an example. By the way, it's a really important example, and again, we'll see more about this in chapters 6 and 7. We don't have the tools to talk about why this is an important example, but it turns out it's extremely important example. Okay. All right, now a little bit of terminology. If you take a gradient, given a function, when you take the gradient, that thing that comes out, big surprise, is called the gradient, because it's what we get when we compute the gradient, the most obvious of terminology. Let's turn that around backwards. Given a vector field, if I were to ask, I want to go the other way. I'm not going to start with a function and take the gradient. I'm going to start with a vector field and ask, what is the function whose gradient is that vector field? Going that other way, I propose it should be called the anti-gradient. And I'm totally stealing grammatical construction there from derivative and antiderivative. Same idea, right? Y'all are familiar with the term antiderivative, right? Sometimes people like to call it an indefinite integral. Problems. But derivative and antiderivative makes loads of sense. This is the exact same basic idea. So I personally prefer to call this thing the antigradient. Now that said, the more common terminology is to call it a potential function. It's not as self-explanatory as to why they call it that. The reason they call it a potential function is because of this reality right here, and that if you were looking at a force, and if you want to understand that force as being a gradient of something, potential energy is closely related to what that anti-gradient is. And so potential function, because this thing that I call anti-gradient is most of what you need to know to understand potential energy. So if you're doing physics, and in particular, if you're thinking about a vector field that is a force, specifically a force, the anti-gradient relates to potential energy and thus the term. Now here's the problem, and I think this is a nasty problem. That function, that thing that I would like to call anti-gradient, that thing that is more commonly known as a potential function, is not potential energy. It's the negative of potential energy. It's so frustrating. It's unavoidable. Let's think about the easiest example we know, gravity. Potential energy is proportional to Z, right? Higher you go, the more potential energy you have. If your potential energy function is Z, the gradient is literally pointing upward. The force is literally pointing downward. That's how gravity works. So the minus sign is that's unavoidable. It is what it is, right? And this works for electric fields and electric potential. It works for any sort of force and any force that has a corresponding potential. The anti-gradient is the negative of potential energy. So So let me now explain. Hopefully this is all, you probably already see where I'm going with this. I find it a little awkward that they call this a potential function. It's the negative of the potential. It's not the potential, it's the negative of the potential. That seems really confusing to me that they give a name that kind of sweeps a minus sign under the rug. Minus signs matter. Right? So this always bothered me. Anyway, heads up, be aware of this, right? I think it's a sneaky little ugly little reality that you have to be aware of. And all of this, of course, goes away if you just use the term antigradient, perfectly natural. Antigradients are the negative of potential energy. Nothing weird about that. Problem avoided. And yet, this is the more common term. So anyway, it is what it is. How we doing? Everybody with me? All right, enough of that. Okay, so we talked about how vector fields can represent forces. That's nice. We also have talked about, we kind of waved our hands anyway, at vector fields could represent flows of fluids, right? And I have talked about a couple of examples. Airflow is an easy and obvious example. Here we are in a three-dimensional room. I hear the air conditioner is on. There's a certain amount of airflow, not very much, but it's enough. It's a good thing. At any given point, if I were to look at this exact point right here, the air has a velocity at that point. So at any point, there's an associated vector. That's what a vector field is. So a vector field is the perfect object, the perfect construction to describe how the air is flowing in this room, or the flow of any fluid, frankly. Okay. I like to point out this one. I think this is a fun one, animal migrations. You can think of animal migrations as the flow of a fluid. Doesn't seem like it's appropriate. Animals aren't fluids, right? Maybe jellyfish? Something? They're kind of liquidy. You don't tend to think of animals as being fluids. Let me try to change your mind on this. Let's think about the stereotypical fluid, water. What's it made out of? Little tiny little particles, right? Much smaller than the scale that we typically think of a fluid. But it's made up out of little bitty indivisible, well, I'm going to say indivisible. As long as it remains water, they are indivisible little particles. Okay. Now let's think about a migration pattern of some species of bird. And I don't mean let's look out the window and oh my gosh, there's a robin, right? I'm talking about big scale, continental scale pictures, right? There's billions, maybe trillions of of some kind of bird out there, and they all kind of flow together. And no, they're not made out of water, right? But they are lots and lots and lots and lots of little teeny tiny little, as long as they remain birds, indivisible little, basically, particles. It's not that different. All physical fluids really are just lots and lots of little bitty indivisible little particles. So when it comes to talking about a migration pattern, again, you're talking about massive numbers of minuscule, teeny tiny little things, at least by comparison to scale. It's a fluid. Does everybody buy it? I think it's kind of a cool point. Okay. All right, so natural question we're going to ask. We'll probably have to, we'll see how far we get. Very natural question, though. Suppose you have a fluid flowing, and suppose we're going to use a vector field to represent the velocity of the fluid. So here, for example, something like that. By the way, in this example, I want to keep things as simple as possible. So let's assume that this vector field is constant, and let's assume you'll notice this piece of surface that I have down here is a flat piece of area. Right, specifically indicated that it's flat. We just want the nicest possible scenario. We will consider non-flat surfaces non-constant vector fields. We'll consider all that later. But, okay, so we have a flowing fluid. We have a flat piece of surface. By the way, I need to talk about how that surface is sitting in space, and I'm going to do so by describing its what we call normal vector. And let's look at my hand. Imagine my hand being a piece of surface, and you can see how I can orient my hand in various sort of different ways. And if I understand the normal vector, then that tells me a lot of information about how that piece of surface is sitting in space. Okay? So that's the job of the unit normal. Yeah. Okay, so the big question we want to ask in this scenario is, what's the flow rate? Let's see here, I'll use this color. Flow rate, so volume per unit time. I've got this piece of surface. Maybe it's think of it as like a screen door kind of a thing. And the fluid is flowing along, and the fluid has the ability to flow through the screen door. And reasonable question, how much fluid per unit time is flowing through that surface? So, volume of fluid per unit time. Seem like a reasonable question? By the way, here's another example. If you're looking for some reason why I would care about such a thing, imagine that I'm fishing and I have a net down in the water. Right, so maybe I have and maybe it's a river, big river or something, and I've just got a net down there. I'd like to know how much water is flowing through the net, because there's a certain amount of fish per unit volume of water. And if I know how much water is flowing through the net, then I can have an estimate of how many fish I'm going to catch in my net. Right, pretty natural, I think. So the calculation is pretty straightforward. What I'm going to do is imagine a certain amount of time. In a certain amount of time, there will be a certain amount of volume that will have flowed through my area. That volume, I just got to figure out how to compute that. I'm going to make a reference to this thing I'm going to call D, the displacement vector. That just says how far has any particle of water traveled while going with that velocity in that amount of time. The water will have flowed a certain amount. And the first observation I'll make is, let's see here, I've lost track of my colors. Let's see here. Let me use yellow for the volume. That volume is going to be the area times that red height. Right, so the flashbacks to high school geometry. Height times the area of the base gives you that volume. And then the next observation is that height is, let's see here. It is the component in the normal direction of that displacement. Right, the displacement is off at some angle, who knows? I don't really care about the extent to which it's leaning over. I just want to know, in the normal direction, perpendicular to the area that I'm interested in, what is that height? And that height is going to be this component of that displacement. And then it's kind of all over with the shouting at this point. Components are computed with dot products. Displacement is velocity times time. Keep in mind the vector field represents velocity. Right? And now, all together, we've got volume per unit time. And you can see right here that therefore flow rate, volume per unit time, is going to be this expression right there. F dot N times area. And this is a very important mathematical construction that we're going to do a ton of stuff with. It's called flux. It's represented with the capital Greek letter phi. Again, the nice, natural, simple interpretation. It's telling you volume of fluid per unit time passing through a surface. Nice, easy interpretation. And by the way, it turns out flux has many other very valuable applications. We'll get to those in Chapter 7. And I'm going to show you another one on Friday. First thing, we'll pick up there on Friday. Y'all have a good rest of your day. See you later.
Thank you.
Yeah, see you later.